What's up, guys? Today we're going to be coding the simulation of the Maclaurin series out of pure curiosity. So what is a Maclaurin series? Well, today we're going to have to learn a little bit of calculus to understand the context of this simulation. But regardless of the context, it's going to look amazing. So let's get into it. Okay, so this is the section where they're talking about that stuff. Okay, so here it is, Taylor series. So here we see a bunch of graphs. So we see a pink graph and a blue graph. So the blue graph is the sine x, it's the function sine x. And the pink graph is the partial sum. These pink graphs are different partial sums of the Maclaurin series of sine x. So what is a Maclaurin series? Well, a Maclaurin series, you can think of it as an estimation of a point on a graph. So right here we're estimating, you see the first partial sum of this Maclaurin series is y equal x. So that y equal x is supposed to estimate what the values of sine x equal around the point 0. So the reason why why we're estimating the point at x equals 0 is because the Maclaurin series is a special type of Taylor series. So a Taylor series is a series that estimates a graph at any point that you give it a. But a Maclaurin series is, the a is specifically 0. Okay, so what we see is the estimation at x equal 1 is very good, but as we diverge from x equal 1, the estimation becomes very bad. See how we're saying that the value is equal to this, but the actual value of sine x is right here. But as we continue down the estimations get better and better. So how do we make the estimations get better and better? Well, we add another term to the series. So here it says y1 equal x is the first term, or the first partial sum. The second partial sum is y2 equals y1 minus x cubed divided by 3 factorial. So we can see that we started out with y1. y2 equals y1 minus something, then y3 equals y2 minus something, and then y4 equals y3 minus something, and then y5, and it keeps going. So we see that they're all connected, and as you keep going down the row, they get better and better until you barely can even see the pink graph. Because the estimation is getting so good at x equals 0 and so good at the points around x equals 0 that the graph is, you barely can even see it. So that's what we want to simulate. So we want to simulate this y equal x becoming this function, becoming this function, becoming this function, becoming this function, and so on. So here in this box we have the Maclaurin series for different functions. So the function we're going to use is sine x, where the Maclaurin series for sine x is this. And this is the equation we're going to use to create this Maclaurin series. And you're going to see this equation later in our code. Okay, so let's conceptualize how we're going to make this Maclaurin series. So first of all, we're going to have data points, right? So we're going to have some kind of object called data points. And then we're going to have an object called equation to use these data points. So if we have y and x axis like that, and to begin with, we just plot a bunch of data points. Let's say we plot 10. So 1, 2, 3, 4, 5, 6. Actually, let's do 20. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, so we have 20 data points, right? And these data points, they know a couple things. Well, they know where they are in the x and y position. So they know that their y's are zeros and their x are whatever. So, and the way that they know this is this equation object is going to say, hey, I have these data points. I have, let's say, 20 data points. So the equation object is like, I have 20 data points. How am I going to arrange them so that I can properly show the Maclaurin series? Well, the way we're going to arrange them is we're going to start with our smallest value and increment our way down by the same increment until we get to our biggest value. So the way that we're going to do that is we're going to have some kind of step, where the equation for step is your x min your x max minus your x min divided by how many data points. So the number of data points you have. So let's say this is -5 and this is 5. We have 20 data points, right? So what is this increment? Well, the increment, like we said, is x max minus x min, where x max is 5 minus a -5 divided by the number of data points, which is 20. So now we get 10 divided by 20 is 0.5. So we know that the increment between these is always going to be 0.5. So the way that we're going to do this is we're going to have these data points, right? And they're going to start at 0, 0. The next thing we're going to say is, data points, I want you to resemble the y equal x function, which is the first partial sum of the Maclaurin series. So it's going to say, hey, data points, I want you to resemble this function. So the data point will say, hey, I don't want to change my x value. I want to keep my x value the same. Based on this x value, if I plug my current x value into your equation, y equal x, what am I? So in this case, you're just equal to your x value. So it goes all the way down. It does not change. And so on until they resemble, until these dots resemble the y equal x function. Okay, so the beauty in this code is not that we can make these dots equal these different functions, so y equal x, then the next Maclaurin series and the next partial sum, which is the next partial sum and then the next partial sum, then the next partial sum. That's not the beauty in the code, that we can make these equal. Because as we saw in the book, we already know those. We already have a visualization of those Maclaurin series. Remember the pink lines. The beauty in this code is watching them travel from where they are to where they need to be, right? So how are we going to make them travel? Well, obviously we're going to add or subtract to their y. So let's say that their destination, right now they're at a y equal to 0. And when they plug in their x value into this equation, their new destination, the destination y is equal to, well, if you y equals, it's actually equal to their x value. So now they travel from 0 to their x value. So for example, this dot would travel from 0 to their x value. So it would be -5. So this is -5 right here, because this is y equal x. So the beauty in this is watching this dot travel from 0 to -5. And how fast do they have to do this? Well, they have to do this at some kind of travel speed, or a certain number of steps. So let's say that we want this data point to travel there in 5 steps. So we want you to get there in 5 steps. So if we want you to get there in 5 steps, how big do each step have to be? And this is different from this step. So let's just call this travel speed. So travel speed is how many steps I want you to take, how many steps to destination. And knowing the steps to destination, we can figure out your y speed. So y speed is equal to where you want to go, so let's just call that y2, minus where you are, divided by how many steps you have to take. So if we did this simple problem, -5 is where you want to go, 0 is where you are. So we type in -5 or -0, and we want you to take 5 steps to get there. So that means that your travel speed for your y is -1. And that's how we're going to implement this. That's pretty much how we're going to implement the equation object and the data points object. And then once it gets to y equal x, it's going to resemble the next Maclaurin series, or the next partial sum, which looks like something like this. Hopefully I can draw this. So once it gets to its destination, we're going to have a function, like we're going to create this, but once it gets to its destination, the minute it gets to its destination, it has to say, okay, I need to do the next partial sum, which the next partial sum, remember, which is the pink graph in the book, looks kind of like this. So the next partial sum looks kind of like that, something like that. Obviously it comes out like this, like that. So then now the dots are right here, right? So let's say there's a dot up here, it's right here. So now instead of it being here, it has to go down to this partial sum, knowing where it is. So it knows where it wants to go, right here, minus where it is, and then how many steps. And that animation, that's the beauty in it. Watching these dots go from where they are to where they want to be. And then the next sum, which kind of looks something like this, kind of. Like that. Obviously it goes to 0, because that's the point we're trying to estimate. And then we watch it go from this point to, let's say, from this point to this point, from this point to this point. So that's the animation we're going to see. So yeah, that's pretty much the conceptualization of simulating the Maclaurin series.